Welcome to lesson 2.5, solving radical equations. Up until now we've been working with radical expressions, and now we're going to be moving on to equations where we're actually going to solve for our variable. So let's dive right in. A radical equation is an equation with at least one radical whose radicand contains a variable. A solution to a radical equation is a root of the equation. We say the equation has a real root. Taking a square root is the inverse of squaring. So to solve radical equations, we must square both sides to undo the square root. So let's give it a try. Example 1. Solve each equation and verify the solution. Part A. 7 equals 5 root x. We need to find the value for root x. So the first thing we want to do is isolate root x by dividing both sides of the equation by 5, leaving us with 7 over 5 equals square root x. Now to find the value of x, we need to inverse the square root by squaring both sides of the equation, which will leave us with 49 over 25 equals x. That is the value of x we found, but let's check to see if we did that right by plugging back in for x with 49 over 25. So 7 equals 5 root 49 over 25. 7 equals 5. The square root of 49 over 25 is 7 over 5, right? 7 equals, our 5's cancel out, and we're left with 7. So we did our solution correctly. Let's do another one. 10 equals 3 root y plus 2 minus 5. So let's get our square root on its own by adding 5 to both sides of the equation to continue isolating the square root. We're left with 15 equals 3 root y plus 2. Now we need to get rid of the 3 by dividing both sides, and we're left with 5 equals square root y plus 2. Now we need to square both sides, and we're left with 25 equals y plus 2. But we're looking for the solution to y, so we subtract 2 by both sides of the equation, and we're left with 23 equals y. That's our solution for y, but it's important to always check that we did our work right, and we're plugging back in for y, and we get 10 equals 3 onto 23 plus 2 minus 5. 10 equals 3 onto root 25 minus 5. 10 equals 3 times 5 minus 5. 10 equals 15 minus 5. And 10 equals 10. So we did the work correctly. Let's move along. Example 2. Solve this equation and verify the solution. So here we need to solve for a. First thing we need to do is collect like terms. So let's put all our radical values on one side of the equation and all our non-radical values on the other side. So moving across the equal sign, our plus 2a becomes minus 2 root a equals 1 plus 5. Collecting like terms, we find 5 root a equals 6. Isolating root a, we get a equals 6 over 5. Now we need to square both sides, and we're left with a equals 36 over 25. But it's important to check, so let's see if we did our work correctly. Plugging in for a, we have 7 root 36 over 25 minus 5 equals 1 plus 2 root 36 over 25. We have 7 times 6 over 5 minus 5 equals 1 plus 2 times 6 over 5. Multiplying out, we get 42 divided by 5 minus 5 equals 1 plus 12 over 5. Collecting like terms, we're going to get 42 over 5 minus 12 over 5 equals 1 plus 5, leaving us with 30 over 5 equals 6, and finally 6 equals 6. So A equals 36 over 25 is the correct answer. So, not all radical equations have real roots. When a value of the variable determined by solving an equation does not satisfy the original equation, the value is an extraneous root. It is a root of the equation formed by squaring both sides, but it is not a root of the original equation. So that is why we always check that our solution works for our original equation, because sometimes it doesn't. Let's look at this example here. Square root 2x minus 1 plus 5 equals 2. Let's go ahead and solve that. Square root 2x minus 1, moving the 5 over to the other side of the equation, we have 2 minus 5. Simplifying, we have square root 2x minus 1 equals negative 3. Squaring both sides, we have 2x minus 1 equals 9. Solving for x, we get 2x equals 9 plus 1. 2x equals 10. Dividing x equals 5. So let's check our solution. Plugging in, we get square root of 2 times 5 minus 1 plus 5 equals 2. Square root 10 minus 1 plus 5 equals 2. Square root 9 plus 5 equals 2. 3 plus 5 equals 2. 8 does not equal 2. See how even though we found a solution, the solution doesn't match the original equation. So this x equals 5 here is called an extraneous root. I'll give you a little hint that we probably didn't notice when we were working through the equation. But when we got to the point where our square root 2x minus 1 equaled negative 3, I knew right away there was a problem, because a square root can never equal a negative value. So this right here was our hint that it was going to be an extraneous root. However, going through and solving and checking is just as fine. Moving along. Example 3. Show that the equation square root 2x minus 5 equals square root x minus 7 has an extraneous root. So to do that, we should go ahead and solve and check our solutions that we find. Square root 2x minus 5 equals square root x minus 7. Must square both sides to get rid of our square roots. And we're left with 2x minus 5 equals x minus 7. Let's collect like terms. 2x minus x now equals minus 7 plus 5. We get x equals minus 2. Now checking, we get square root 2 times 2 minus 5 equals square root 2 minus 7. Square root 4 minus 5 equals square root minus 5. Right here, big no-no with the square root minus 5. We have to stop there and say, does not exist. We cannot square root a negative. In this case, to have a solution, we would need our 2x minus our 5 to be greater than or equal to 0. So solving that, we would need our 2x to be greater than or equal to 5. Dividing by 2 both sides. Need our x to be greater than or equal to 5 halves, or our x minus 7 to be greater than or equal to 0, having our x be greater than or equal to 7. Comparing these two, we would have a final answer of having our x being greater or equal to 7. This is the only possible situation where we would have a correct solution. Do another example. We have a word problem here. An observer in a hot air balloon that is attached to the top of a 200-meter tower whose base is at sea level. How high above the tower must the balloon be so the observer's distance to the horizon is 100 kilometers. The formula d equals square root 13h can be used to estimate the distance of the horizon in kilometers. So let's let t equal the height of balloon above the tower, and h equal the height total. So since d equals square root 13h, and we know that the height total equals the height of the balloon above the tower plus the 200 meters of the height of the tower. Sub in d equals the square root of 13 onto t plus 200, which equals 100 because of the distance to the horizon. Now we need to solve for t. Let's get rid of our square root by squaring both sides first. Now we're left with 13 onto t plus 200 equals 10,000. Then divide by 13 on both sides, and we're left with t plus 200 equals 10,000 divided by 13. Solving for t, we get 10,000 divided by 13 minus 200, and t is approximately 569.2307, etc. kilometers. Hence, the balloon is about 570 kilometers above the tower.